Thank you. Yeah.
Thank you, everyone. Thanks for coming. So this is okay, it's a fancy title, but basically it's going to be a no-go result for achieving constant round black box zero knowledge protocol, even if you try to use quantum information in your protocol, on this protocol. And this is joint work with Jiahui, Kaiming, Xiao, and this is mostly done while I was at MIT, but currently I'm at Fujitsu Research. So I think, so let's start with the basic definition of interactive proof system. So in interactive proof, there's a prover and there's a verifier. They both see some kind of instance, which is public information, like a graph. And the prover wants to say, okay, this graph is three-colorable. It wants to prove it to the verifier, and the prover holds a witness to how to three-color the graph, and the verifier has no idea. But the thing is, the verifier in the end at the end of the protocol would output accept to say, okay, I'm convinced that the graph is three-colorable, or reject to say I'm not convinced. So there are several properties we want to guarantee in this proof system. The first is completeness, is that, of course, when the graph is actually three-colorable, the verifier would output accept, and hopefully with probability 1, maybe minus some negligible error. And then it comes to the first security notion people care about, is that, of course, we need to guarantee that when the graph is not really three-colorable, the prover doesn't get to cheat. So suppose there's a prover that tries to convince the verifier on some non-three-colorable graph. We hope that the probability that the verifier outputs accepting the end is negligible. And cryptographers usually would care about a third property that's called the zero-knowledge property. In the zero-knowledge property, we imagine there is a malicious verifier that tries to not only just learn the fact that the graph is three-colorable, but actually wants to learn how to three-color the graph, which is probably some secret information that the prover doesn't want to reveal because it's probably a secret key that it can be used to authorize something. So the zero-knowledge property is a property that we want to guarantee the verifier learns nothing except the fact that the instance is in the language.
Is the prover cheating here? Or the verifier?
Oh, the verifier, right?
The prover looks cheating.
Oh, I mean, it's a very innocent.
The prover looks like some don or some criminal.
Yeah, that does look a bit, yeah. But in fact, oh yeah, it's just a meme. Like if you know this guy on the left, it's a bad guy. It's from this movie called American Psycho, where he kills a lot of people. So yeah, sorry for putting up a niche meme. Hopefully it's not niche. Okay, let me grab my water. So how do we more formally define zero-knowledge property? Is that we want to define feel like something it's not showing up. It's okay. So we want to define it through simulation-based definition. Is that there is a real world where a prover and a verifier interact, and they would output a communication transcript that shows, okay, this is what the messages we exchanged in our protocol. And there's an ideal world where instead of prover, there's a simulator, which is shown as a typewriter here, that interacts with the prover in some sense. I will tell you how it interacts. And in the end, it would also output a transcript. And hopefully these two transcripts are indistinguishable. Okay, zero-knowledge protocol has a lot of applications. So for real-world applications, I think some of us know that they are a special case of multi-party computation. They lead to also identification schemes, and also they are using blockchains nowadays. And more generally and foundationally, they also have a lot of implications to other fields of theoretical computer science. And for this talk, I will focus on 3 properties of zero knowledge. The first is black box property, and I will explain what that means. The second is round complexity, and the third is efficient simulator, where there's a difference between expected polynomial time and strict polynomial time. Okay, so what does black box mean? So just as I mentioned, in the ideal world, the simulator will interact with the verifier in some sense. And when we do a black box zero knowledge protocol, I mean that the simulator is only running the verifier as a black box. It means that it only gets to see the input output behavior of the verifier instead of actually accessing its code. So why do we care about black box zero knowledge? Basically, there are a few reasons, but they are all very important. Like actually, most known protocols do satisfy black box zero knowledge property. And indeed, sometimes non-black box simulation technique would help us achieve something that's not achievable in the black box setting, but there are only very few known non-black box simulation techniques. And also protocols with non-black box simulations are usually much less practical. They're more complicated and inefficient. And the second property, I think it would not be very hard to imagine. It's around complexity. Of course, for efficiency reasons, we do not want there are too many runs in their interaction. Hopefully, like everything can be done in constant runs.
So one second, black box simulator just means that the simulator only has Oracle access to the prover.
Yeah, exactly. Oracle access.
Verify.
Yeah, verify. Yeah, I mean,
Oh, sorry.
yeah, it's
Yeah,
just
right,
a
right.
slip of tongue. Yeah, I know what you mean. Yeah.
But usually we need like rewinding and proving sounds, right? So
Yeah,
we only have black box.
yeah, in black box, but you can rewind. So you just imagine the verifier as a verify function. You just feed in some message and it would output the next verifier message. But you can rewind by saying, okay, yeah, I will go on to that details later. So you can rewind and say, okay, I just asked you my second message, but now let's go back to the first message. I will just ask another message. But
That's kind of
but you are all
rewinding.
using it as a black box. So you're not seeing anything other than the input output. And the third property is strict polynomial time. For strict polytime simulator, it runs in polytime even in the worst case. But for expected polytime, we say, okay, maybe there's a small chance that the simulator actually needs exponential time to finish the simulation, but let's say that's okay. We just average over things and we are still polynomial time. But indeed, strict polytime is still better because you don't get to really run into the worst case. Okay, so what are some results for classical zero knowledge? So for now, everything is still classical. So there's this I think the seminal work where they put forward zero knowledge. They have poly runs, and everything is and okay, it's also proof. Like the difference between proof and argument is that whether the soundness is computational or statistical. But for this talk, that's not the focus. We will just say, okay, computational soundness is fine. And they only need one-way functions for their assumption. And then it's improved to be constant round and also black box. But the thing is that all of these constant round protocols, they only have expected polynomial time simulation. And in fact, there's a seminal result by Barak and Lindahl that shows that you simply cannot achieve all these above 3 good properties I mentioned to you all at once, unless you are just proving a trivial language. So that says there does not exist constant round black box zero knowledge protocols for NP languages with strict polynomial time simulator. So as we will see in the proof, that all of these properties will show up in this result. And of course, we, for BBP, like there's not much interesting thing here of like doing it because the verifier could probably just do it on its own unless you want like succinct proof, but that's another story. So constant zero knowledge requires either non-black box simulation or expected polytime simulation. That's the message here for classical protocols. And now we move to the quantum world.
So how restrictive is strict polynomial time? Because like, for example, like the classic recoloring protocol doesn't have a strict polynomial time simulator, right? because you need to keep rewinding. You need to hope the verifier keeps making a guess that you can win.
You mean like the GMW protocol?
Yeah.
Uh,
I think so.
Yeah, like the exact protocol doesn't have so it's because it's at first it's a polyron protocol, and also yeah, I actually don't quite remember about the details here.
Okay.
But let me see. So I mean, whether there's a strict polytime simulator. Oh yeah, I think this one it actually does, right? GMW should be strict polytime.
Because the challenge space is very small.
Yeah, I think the thing is you basically just
This is a sequential repetition of the basic sigma protocol, right?
yeah. Just a sequential repetition.
But like you could keep getting the bit you don't want. Like the probability is exponential. But there's a
The chance of not getting the bit is like roughly half.
Right, it's only
You doing it like a lot of times.
and you expect to get the bit, but this is like expected polynomial time, not strict polynomial.
You can abort if with some probability if
Negligible. Okay, maybe we can go into this later.
yeah, we can go on to this later.
So with fiat Shamir, why do we care so much about the number of rounds? This seems.
Oh, the thing is that's in a different model. So fair Shamir, you have random oracle, right? So which is like
This is low, right?
yeah, this is without random oracle and no CRS. So non-interactive is a completely different story, because you have to start with some CRS or random oracle, which is in some sense more powerful than CRS, right? So okay, so let's move to the quantum world. So at the first step, maybe something to wonder, to ponder over is for classical zero-knowledge protocols, are they still secure against quantum adversaries? I guess that's something cryptographers would care about in the first place. And how do we define zero-knowledge protocol secure against quantum adversaries? We say that okay, when we talk about zero knowledge, let's say our honest parties are still classical because they don't cheat. But you never know what the malicious party is doing. They might be secretly using some quantum computer at home. So let's say since our malicious party is the verifier, now we care about a quantum verifier. And in order to create this simulation with the quantum verifier, as I mentioned, the simulator has to interact with the verifier oracle, which is some circuit. Now it's a quantum circuit, so naturally we let the simulator be quantum as well. So in the real world, there's a classical honest protocol and a quantum malicious verifier. And in the end, they output a classical transcript. And in the ideal world, there are quantum simulator and quantum verifier oracle. But in the end, they still need to output a classical transcript so that these two are indistinguishable. So, okay, one question is, okay, does classical ZK, if we just replace every component in the with post-quantum secure assumptions like lattices, does it directly give us post-quantum ZK? Let's look at a sequence of results on this. So it turns out that in order to show ZK against quantum verifiers, there's indeed more technical, it's very technically different. You have to handle it very differently. So for the three coloring, I think you can, there's the first protocol, first proof by Watrous, where you can achieve polyround, because in his protocol, okay, there's the constant round protocol where you only have constant soundness, and in order to reduce the soundness error, you have to sequentially repeat it. But it's a very, very elegant proof. And then there came this result after 15 years, a non-black box simulation, a protocol that is constant round, but that requires non-black box simulation. That's it, built on quantum security of lattices, LWE here, and quantum fully homomorphic encryption. And also simultaneously, some work came out, another work, CCY 2020 came out that achieves constant round as well. But the thing is, the caveat is that they only achieve a weaker version of the zero knowledge called epsilon ZK. Even though they do have the advantages that it's a black box simulation. So it's basically just taking the classical protocol, the classical protocol, constant round protocol that's shown to be secure with expected simulator and replacing it with post-quantum assumptions. But the thing is that they can only prove it's epsilon ZK secure, which means your simulation quality, instead of negligibly away from the real world, it's epsilon away from the real world. So
simulator runs in 1/epsilon.
Yes, exactly. So simulator runs in 1/epsilon. So it means the better you want to simulate, the longer you have to run. So if you want to do negligible, you will run in super poly time. So that's the
Can you
caveat.
say a bit about what the non-black box simulation, how does it work in quantum setting? Like,
Oh, okay, cool. So let me just go in briefly. So in fact, this technique, this non-black box technique is not entirely new. It's used in classical as well. It's used in this alternative proof of impossibility for obfuscation, where so basically, as I mentioned, there are only very few non-black box techniques. So in fact, there are only two. So the first one is diagonalization. When you get to access the code of the verifier, you can somehow design it so that you can run it on its own code in some sense, and that would somehow trigger the verifier to output something that you would not get if you are only interacting with it black boxy. Okay, that's the first technique, but you cannot use that in the quantum world because the verifier is not clonable. It's not necessarily clonable because it's quantum. So you cannot always just copy its own code and fit it in onto its own. You cannot do that in general. So there comes the second technique that's also used in classical world, is that actually I can homomorphically encrypt the code of the verifier. Then I homomorphically evaluate it on some auxiliary information that I have from the protocol. After that, it would output something, some hidden secret which I cannot see if I only use it as a black box. So that's the idea.
this idea is in classical land, there was this paper by Vitansky, Dakshta, and Homer. Is it adaptation?
Yeah, I think that's the classical version of it. And then this is, and Vitansky is also on this paper, the quantum paper. So okay, so the first question is, okay, after seeing all this, maybe the first question is to ask is a constant round post quantum black box zero knowledge protocols. So actually, intuitively your answer may be no, because we don't even have that for classical malicious party. So now we have a quantum malicious party. Things can only get even more challenging, and basically that's true. It's just that the proof wasn't very easy to go from just, you can't simply use a classical proof against quantum adversary. You have to use a new proof. But the thing is, there indeed does not exist the constant round post-quantum black box zero knowledge protocols for NP. But and the other surprising thing about this result is that this even extends to the expected polytime simulator. So this no-go result not only holds for strict polytime simulator in the quantum world, it also holds for expected polytime simulator. And unless you work in a different, philosophically different mode, where I won't have time to go into details for that. But basically, for a regular model, where if you consider the running time, of the simulator to be a piece of classical information instead of a quantum information, let's just say that this constant round black box ZK impossibility extends to even expected polytime simulator. And this actually demonstrates a difference between classical and post-quantum ZK. And actually, this sort of corresponds to what I just said. It's actually related to the fact that the quantum simulator can come with a quantum state, which is not used in the proof if it's classical. So this also complements the fact that we either need non-black box simulation or we need this weaker epsilon ZK thing. Okay, so I guess one natural questions, I guess both the quantum community and crypto community would ask is, so why not try giving honest parties more quantum power? So right, so if we only have classic honest parties and quantum malicious parties, it only makes things harder. And why not just use magic against magic? And is it possible to have a constant run black box ZK now?
Sorry, so what is the change here? What did you change in?
Okay. So the first result is that this result is for classical protocol security against quantum verifier.
Okay. I see.
So
So is your adversary quantum or classical?
yeah, right now adversary quantum, honest party classical.
Okay,
And now I say honest party quantum, adversary quantum.
okay.
Okay.
But the functionality is still classical. You want to
Yeah.
prove a classical statement.
Yeah. So we want to prove a classical statement, but you can also think about more general statements like QMA.
So your previous slide had, unless you consider some other expected polytime model, what is the other expected polytime model?
Oh, okay. So I don't think I have time to go into details, but let's say on the high level, in this model where expected polytime simulator is impossible, we are assuming that the information about the simulator's running time is classical. So basically, you run the simulator, and from time to time, you would sort of just suppose there's a register that keeps the number of steps it runs. You would just measure that register from time to time. It actually shows up in their proof. But for this different model by LMS 2022.
Fermi.
Yeah, Fermi, Lombardi, Spooner paper. Yeah. So you are keeping that information as quantum information. And what they say is, okay, so this time is kept coherent, you don't measure it. And maybe there is actually a branch of the simulator on this time register that actually runs to exponential time. But if you amortize over the weight of that quantum state, it's polytime. That's their new definition of expected polynomial time. So yeah, if you work in that model, you do achieve expect polytime simulation.
Is that class interesting? Does it solve hard problems? The
I mean,
class of simulator just created.
I mean, that's of post-quantum expected polytime simulation. I think they have a few other results, but
No, I'm asking.
oh.
You're disqualifying this. The question is, what is the consensus? Is that class closer to expected polynomial time, or is it closer to being something like above in the complexity hierarchy? Is it a powerful class, or is it? I mean, we would want simulator to be as efficient as possible, meaning it should be in relatively low complexity class.
Yeah.
My question is this coherent or whatever they call it, right?
Yeah, coherent running time.
Yeah. So
yeah, good question. Actually, I'm not sure. I don't think I haven't checked follow-ups on that work. Yeah, it's a good question. So yeah, I don't know how powerful it is. But intuitively, it doesn't. I think that some people have complained about this simulator being not very physical because when you run it, there's actually a branch that's exponential time. So it's like it's more like mathematically interesting than like physically implementable. I think that's one issue, but I don't know just mathematical wise how powerful that is. Maybe it's not like super crazy. It's probably like philosophically close to classical expected polytime in some sense. Yeah, it's just not physically very practical. Okay, so so what's a fully quantum ZK? As I mentioned, now we have honest parties quantum, malicious parties quantum. So in the real world interaction, the prover and verifier would output a final quantum state. And in the ideal world interaction, the simulator and verifier would output a final quantum state because right now the product is no longer classical. So in order to simulate, to consider like the most generic way of describing a quantum interactive protocol, your final output of the entire protocol would be quantum, because even your messages exchanged in the middle will be quantum. And okay, the simulator right now needs to simulate this quantum output. So let's look at some existing protocols. For NP as well as QMA. So QMA is actually the quantum analog for NP. I think Hao asked about it. I will get to that later. So in fact, it's enough to care about NP for the focus of this talk. So black box, there are black box protocols, okay, but they all require polyruns. There's also constant run protocol. Actually, this BS20 paper, one using QFHE and LWE, they actually it can extend their protocol to work for QMA. There is also constant run and black box, the one I mentioned as well. They can also achieve QMA, but still weaker zero knowledge guarantee. But why do we think quantum honest parties can make things more powerful, can achieve better protocols? Because there's actually a bunch of evidence that shows quantum information actually helps you build crypto. So quantum are not always malicious. Sometimes they help you do things as well. For example, I think the famous protocol is called quantum key distribution, which basically means key exchange, whereas you need structured computational assumptions to achieve this notion. Classically, quantum, you can, almost do it information theoretically. Okay, so, and there's amazingly also a belief-based transfer, and of course, which leads to MPC, that you can just build on one-way functions. And in the classical world, you also need structured assumptions. And there is also some work that show using quantum information to collapse the number of runs you need for interactive protocols. So this does give us a lot of hope for using quantum to reduce runs in zero knowledge as well. However, unfortunately, we show that
MPC is malicious.
The
MPC is malicious.
What malicious?
You get malicious MPC with quantum information and one-way functions.
Yeah, I think so. Otherwise, it won't be too interesting.
Because that will imply ZK.
Right. That's not constant. Right. It's just the better assumptions because they just build on one-way function. Yeah. Okay. So in our case, we show that for our particular setting where we want to achieve this best of three words ZK, fully quantum protocol, honest protocol does not help you. So there's simply, the formal statement said there simply is no constant round fully quantum BBZK for QMA. And of course, that would imply NP. Sorry, not imply, it's in fact, we showed it for NP, but since it's a lower bound result, it implies for QMA because QMA is a larger complexity class. If you don't have a protocol that proves languages in NP, you don't have it for QMA. So unless QMA is in BQP. So as I mentioned, QMA is the quantum analog of NP, and BQP is the quantum analog of P. So basically, we don't believe this is true. And also respectively, if you care only about NP, this impossibility holds unless NP is in BQP. Even though we know quantum can do lots of stuff, but in general, people don't believe that they can solve NP complete problems. So usually we believe that NP is not in BQP. So this result holds for both strict polytime simulator and the expected polytime simulator. Still, unless you work with a different with this coherent running time model, you can do expected polytime. And also, as I mentioned, our proof is for NP. It would imply QMA because it's a lower bound result, and this justifies the non-black box simulation and the need for weaker zero knowledge. Okay, so for the rest of this talk, I will focus on how we prove this result for strict polytime simulator in the fully quantum setting. So for the rest of the talk, I will first give a high-level review on this seminal result by Barak-Lindow, the classical predecessor, because I know that most of us here probably not very familiar with quantum, so I will try to make everything as classical as possible. And I think it still suffices for the understanding of the high-level techniques. And then I will mention how this CCLY paper, the one that shows the same result for post-quantum setting, for classical honest party, quantum malicious party setting, how they lived that result from Barak-Lindow to the post-quantum setting. I will mention how like some of the benefits of a fully classical protocol helps the proof go through, and that would show some of the barriers when we want to do the proof again, when we have a fully quantum setting. And finally, how we overcome these barriers. And this is going to be oversimplified because it's going to be too technical. Okay, so let's go over what does it mean to simulate, right? So in order to simulate, the simulator does not have the witness. It has to be given some other superpower in order to convince the verifier. So classically, the simulator is given the power to rewind the protocol. As I mentioned, it only interacts with the verifier. Okay, so right now they are shown to be quantum, but in fact, sorry, I forgot to remove these atom symbols. Just ignore them. So let's imagine the simulator and verifier to be classical right now. So it interacts black-boxly with this verifier function. The verifier function takes in some prover messages, which it doesn't know, okay, whether it's coming from a simulator or prover. It just, okay, sees the message, it parses it, and outputs a next verifier message. But what the simulator can do is that, okay, can query, for example, on the first prover message, and it gets back a first verifier message from the verifier oracle. And it can, okay, it generates a second prover message. And now it gets back, but the simulator said, okay, I think I tried a bad message. I have to try something else in order to simulate. So it goes back and query again on a different prover message. So that's the power it gets. And the high-level approach of Barak-Lindow CCLY, as well as our paper, the idea is that we want to make sure that in this specific protocol where we only have constant round and black box and strict polytime, the simulator doesn't really learn much by rewinding. So basically, what we want to show is that the simulator essentially would act as an honest prover because rewinding doesn't help it. So more specifically, the first step is that we would design a specific malicious verifier VSTAR. And by our definition, it says that, okay, a successful simulator must deceive all possible malicious V. Then it must be able to deceive our specifically designed VSTAR as well. But if it can do so, we can turn the entire interaction of the simulator and VSTAR into a BQP decision algorithm. That means on any input in the language, the entire if I simply run the entire intersection, which is polytime, it would output one with high probability. And given some instance not in the language, it would output one with negligible probability. So that means basically I have the simulator algorithm, the VSTAR, and none of them has the witness, but given arbitrary instance, it just helps me decide whether it's in the language. So now it's a BQP algorithm. And classically it's a BPP algorithm.
So for the second step.
Okay.
When you say the successful simulator deceived V, it's only for like a true state when X is in there.
Oh yeah, I mean deceive V in the sense that it can just it can always simulate the view of the verifier.
No matter the statement is in here or
not. Right, yeah. If it's not in the language, it shouldn't be able to make the verifier. By deceive, I mean, okay, this is just not formal. By deceive, I just mean it simulates the view of
you can always create
it always create the transcript that's close to a real world interaction.
writing is useless.
Yes, the intuition is that rewinding is actually useless. But of course, I mean, it's useful for general, you want it to be useful for general protocols, but here we want to use this intuition that for this specific type of protocol we want, where we want all these good properties, we will see that in fact we can design a malicious verifier that so that the simulator's queries are rewinding queries are made useless. So intuitively, since the simulator's queries is only polynomial, it's not able to see two forking transcripts in its interaction with the verifier. So essentially, you would have to interact with the verifier in a straight line fashion, just as the honest prover does. So the kind of simulator behavior I mentioned earlier, like if you are not satisfied with your current queries, you want to query on something else, you wouldn't be able to do so. So how is that achieved? So this is achieved by designing this random terminating V star that on each prover message, V star would abort with a relatively high probability. So it's not too high. I mean, if it's too high, it would always reject. It would never get accepted. But you still wanted to proceed the protocol with inverse poly probability. But otherwise, with all this 1 minus inverse poly probability, it would simply abort. It would just say, okay, I just don't like you for no reason. Let's stop the protocol. Like, but when not aborting, the V star would act like an honest verifier and proceed and say, okay, I kind of like you. I'm going to output the next prover, next verify message, just honestly. So this is the design of the V star. Okay, then how is that? How does that help us build this BQP algorithm? Okay, so the correctness. So the first thing is correctness, right? So we say we can use V star and our simulator to decide any BQP language. Then given any X in the language, running this interaction, right? As we know by the zero knowledge property guarantee, it's going to be close to the interaction with of V star with a real prover. Since we know that with the honest prover on this language on this instance in the language, it would output 1 with probability epsilon to the k, because as we have seen here, there's a for every message there's a epsilon probability that V star is not aborting and simply proceeding, and k is the number of runs. K is a constant. So at the end of the day, even though V star is aborting with high probability, still we can still get to the end of the protocol with epsilon to the k, which is inverse polynomial. Okay, of course, the simulator, since it simulates this view perfectly, it also gets to the end of the protocol with epsilon to the k minus some negligible simulation error. And this is noticeable since this is a noticeable amount since we have a constant k. Okay, now it's left to show that when X is not in L, this would output accept with negligible probability. So the idea is that we would have this external honest verifier V, and we want to say if there's actually some a simulator that actually can make the V star accept in this case, then we can build a malicious P star, a malicious prover that actually breaks the soundness of our protocol, which we have the premise that the original protocol is sound. So how does that work? When X is not in the language, we imagine there's some malicious prover. It pretends to be V star and X interact with simulator. And okay, so when the simulator and also it's interacting with the external honest verifier that it tries to cheat. So P star would pass the unaborted message. So P star would act like V star, so which means it would abort with high probability. But basically it helps that, okay, there simply happens to be K messages that are not aborted, that those happen to be the message that it can forward to the external honest verifier and gets an honest verifier's next message back and feed that as an answer to the simulator. So this is basically you can, by designing this aborting probability in this way, you can basically guarantee that it just happens that there are K messages unaborted and all the others aborted. And you hope that these K messages happen to be the useful message and you can pass to the external verifier. And since, as we said, okay, if the simulator can convince the V star on something not in the language, then we can simply use, since well, what we do is simply passing the simulator message to external honest verifier. We know that we are going to deceive the external honest verifier as well, with some loss in probability. But that is still okay because it's multiplying an inverse polynomial, and that would break the soundness. So this is the idea here. And now we will move to the quantum world. Let's first imagine, let's still staying in the simpler setting where our V star is actually classical. So this is actually used in the proof of CCLY21. So in their proof for the strict polytime, even though V star is actually not really quantum, it's still actually the same V star as designed in the classical setting, but it can be queried in superposition, and this makes things harder. Okay, as I mentioned here, the verifier function of V star is a deterministic verifier function, because you can imagine it's a classical function. You can imagine that there's the randomness tape is fixed as part of its input. But the tricky thing is that now the simulator can query V star in superposition. So just for like a crash course quantum, like in superposition means like not right now I query on not just message M1, I can query on a superposition of M1 and M1 prime. And okay, why does the analysis become harder? Because I used to say that the V star would abort on messages, on some randomly chosen messages. And okay, maybe it decides to abort on M1, but not on M1 prime. So right now I am in superposition of aborting and not aborting it. And what should we do? Okay, that's the tricky part here in the analysis of the quantum setting. Okay, but magically there is this very interesting quantum random oracle technique called measure and reprogram. And basically the technique is already in the name, is that right now I'm going to let V star use a random oracle to decide whether to abort. But I'm going to measure randomly K messages, and I'm going to reprogram the random oracle on those messages and to make sure that they are not aborted, and I would answer these messages. And this is actually very much an analog of the classical setting where you have these randomly guess queries of the adversary and reprogram the random oracle. Here, the quantum version is simply guess the queries, measure the query, and reprogram the oracle. And in fact, this would actually work well for this setting because you only have to guess constant many messages, and you would have a similar analysis to the classical case where you guess constant many messages. Okay, in the soundness side, it's kind of similar. Is that we're going to turn the quantum simulator into a cheating prover. Okay, the prover is the intuition is the same as classical. The prover is going to measure. It's still going to simulate it. It pretend itself as V star in some sense, but it's going to measure constantly randomly chosen constant messages from the simulator and send those out to the external verifier, because external verifier is honest and classical. It's only going to take classical messages. And you have to measure those queries from the simulator. But as I mentioned, we have this magical measure and reprogram technique when you model everything in the random oracle model. And that's fine because we are using black box. We're using black box simulation. And okay, and if you happen to guess the correct messages, simply measure and pass them out to the external verifier and pass back the answer. You are going to simulate the view of the V star. Okay, finally, I have explained how CCLY21 works. The thing is, as I mentioned, there's one very important part of CCLY that their honest parties are classical by nature, and the honest protocol is classical by nature. Which means, okay, when you measure something, when you measure a query, you get a classical message that's a well-defined classical message, right? For example, it queries a superposition of commitment messages. Then when you measure, you get one of the commitment messages. So it's still like well-structured, something that makes sense when you measure. But in the fully quantum setting, the honest messages are quantum. So for those who are probably not familiar with quantum, let me briefly explain. When the honest protocol is quantum, your messages can look like all kinds of crazy stuff. For example, there's something called hard random quantum state, where where it's like a quantum analog of truly random classical messages. But when you measure this kind of state, you would get nonsense. So we get a random string. That's the state is useful when you process it quantumly, but if you measure it, you probably just don't get anything useful. So it's not well defined anymore. Like what happens if I just measure the message and what do I get? Okay, and that's the first issue. The second issue is that the verifier's function, okay, in the CCLY protocol, the verifier function is still classical and deterministic. As I mentioned, you can always just fix the randomness tape. But in the fully quantum setting, there is no such de-randomization trick. You cannot de-randomize a quantum algorithm by taking out its randomness and run it on as part of the input, because quantum are inherently random. So this property helps. How does it help? This is our Y proof. Is that the verifier? Okay, so for example, as I mentioned, the verifier decides to abort using a hash function modeled as a random oracle that would output 0 on anything with probably 1 minus epsilon. This random oracle can be querying superposition, but its functionality on M is only well defined when M is classical. And the second thing is, okay, well, verified function is classical and deterministic. We know that when not aborting, the V star we design, even though it's malicious, but it's in fact not malicious other than aborting. When it's not aborting, it acts just like an honest classical verifier. So it's actually well behaved, which means we can fix its randomness type and turn it into a determinist algorithm that we know how to analyze. And the simulator, when the simulator also, there is importance in the consistency of its behavior. When the simulator makes the same query more than one time, it always gets same response. So the simulator queries, when the simulator queries and rewind and modify history would abort. And all these properties are important in the soundness proof in the post-quantum setting with the classical honest protocol. So this leads to the barriers in the fully quantum setting. First, barrier 1, honest messages are quantum, no well-defined aborting behavior. Like what does it mean to evaluate a hash function on a quantum arbitrary quantum state? The barrier 2 is that honest verifier is inherently random, cannot be de-randomized, and a lot of analysis doesn't go through. Okay, so how do we resolve these barriers in the setting? So let's resolve barrier 1, which actually we just take a very simple approach by simply dequantizing the communication of the honest protocol. So we can't really dequantize it completely, of course, because then what's the point of using quantum power? So you do have quantum computers still at home, but the thing is, now I say your messages are going to be classical. This is done via something called quantum teleportation. So quantum teleportation says that if my prover and verifier, honest parties, so for now, they are going to share some EPR pairs at the beginning of the protocol. And now I can simply turn any fully quantum protocol into a protocol in this model where they use entanglement, but they only use you send each other classical messages. So this is actually a quite standard quantum thing, but here just take the takeaway message that when you have entanglement, you can simply use this entanglement together with classical communication to replace any need of quantum communication. So now classical communication, but on their own end, prover and verifier still doing quantum computation. Okay, so there are some small subtlety when we do this protocol because some people may say, okay, actually using entanglement is quite powerful. You are actually turning the before that there was no pre-shared entanglement. Right now introduce pre-shared entanglement that actually probably leads to more powerful protocol. But the thing is that we work in this very specific model where we call non-programmable EPR. The simulator, when the simulator does the simulation, it will not try to modify this shared entanglement, but it would only use it in a sense that an honest prover would also do. So it would use the shared entanglement honestly, just as the prover does. And we would show that any zero-knowledge protocol in this non-reprogrammable EPR model would imply a zero-knowledge protocol in the fully quantum model. So that's why, so from now on, we're going to showing possibility result for this ZK in the NEPR model. Okay, right now we have resolved the issue of the messages being quantum. We have turned the messages into classical, but still that's actually a very superficial solution. It doesn't really resolve anything because V star inner computation is still quantum. As I mentioned, when not aborting, V star would actually act as an honest quantum verifier. And we also introduced pre-shared entanglement. Does that make the whole thing even messier? Okay, so finally, I'm just going to give oversimplified intuition ahead. So we are going to go back to the intuition that rewinding is useless in what people did with the classical setting, where we want to see that whatever the simulator can do in this kind of simulation, they essentially is only able to act in a straight line fashion, that it only gets to query K useful messages, gets back K answers from the verifier. Otherwise, no rewinding can help. Otherwise, it always gets aboard and sees nothing useful. We're going to mimic this intuition in the quantum setting. So one important thing in this to realize, to actually implement this intuition is that recall the part of the proof where we reduce to the soundness of the honest protocol. We want to show that, okay, P star does not answer any queries other than those answered by the external V, right? Because P star does not have the random tape or in our quantum setting, the inner quantum state of the external V. So it can't really answer any other messages other than those that would be answered by V, by external V. And how do we realizing that in the quantum settings, we quantizing this intuition by actually looking to the interaction state of the simulator and the verifier. We're going to actually see that there's going to be a good branch of the quantum state. I'm putting a bracket on it because it's actually, this branch can consist of many different quantum states, but it's going to be something we call good. It's going to satisfy certain property. In this good branch, the simulator would essentially interact with the verifier in a straight line fashion. As we mentioned, this is what we need to make the entire proof go through. But in the fully quantum setting, there's also this bad branch, which we will see that consists of garbage states and that from aborted message, and also there's all these all kinds of possible simulators, malicious rewinding behaviors that try to rewind you, extract information from you, but we are going to design our verifier so that everything that's done maliciously is going to push into the bad branch. Okay, so this is the joint state of the entire system of simulator and verifier, and it's going to be divided into these two branches. And why is that helpful? We will see that the V star would only use the state in the group branch in the end to decide whether to accept the input instance X. And the band branch, we do need some very careful handling and show some of its properties, but the high level idea is that at the end of the day, the V star actually can ignore the band branch by acting on it using a dummy operator. And in fact, it's simply doing nothing. By dummy operator, I say, okay, it doesn't do anything for the messages on the band branch. And that would help, that would not help the simulator learn anything. So, okay, at the very end of the day, the final state in the good branch will be exactly the same as the final state of the external honest verifier. And the final state in the band branch, it won't contribute to the probability that V star outputs 1. So V star essentially would just be using the group branch to decide whether to accept an input instance or not. And that is the quantized version of the intuition that rewinding is useless, because all kinds of malicious rewinding is going to push into this band branch where the V star would not act on. And the good branch will be exactly the same as as some honest verifier would generate when interacting with a prover. Okay, so that's the end of this talk. I'm happy to take questions, and please read our paper if you are into quantum. Okay.
Right, thank you.
Thank you.